In this example, we will find the general solution to y double prime minus 4y prime plus 4y equals e to the 2t. The associated homogeneous differential equation for this example is y double prime minus 4y prime plus 4y equals 0, which has a characteristic equation of r squared minus 4r plus 4 equals 0, which gives a repeated root of r equals 2. So the general solution of the associated homogeneous differential equation is y sub h equals c1 e to the 2t plus c2 t e to the 2t. To solve the non-homogeneous differential equation, we'll need a particular solution. But notice that y equals a e to the 2t cannot be a solution to the non-homogeneous differential equation as we've seen before, because it is a solution to the associated homogeneous differential equation, and thus y double prime minus 4y prime plus 4y equals 0 for a e to the 2t. So it cannot be equal to e to the 2t. What we saw before is that we should instead use at e to the 2t. But again, this is a solution to the associated homogeneous differential equation. So it also will not work as a particular solution to the non-homogeneous differential equation. So we need to extend this trick and use y sub p of t equals a times t squared e to the 2t. Taking the first and second derivatives here to use in the differential equation, we get yp prime equals 2a t e to the 2t plus 2a t squared e to the 2t. And taking the derivative again, we have 2a e to the 2t plus 4at e to the 2t plus 4at e to the 2t plus 4at squared e to the 2t, using the product rule on each term. And this can be simplified as 4at squared e to the 2t plus 8at e to the 2t plus 2a e to the 2t. And using these in our differential equation gives at squared e to the 2t plus 8at e to the 2t plus 2a e to the 2t from yp double prime minus 4yp prime, which is 2at e to the 2t plus 2at squared e to the 2t, plus 4y, which is at squared e to the 2t. And in our non-homogeneous differential equation, this all must be equal to e to the 2t in order for y sub p to be a solution. But notice here, as in the case when we needed to use the particular solution of t e to the 2t, the terms including t squared e to the 2t and t e to the 2t sum to 0. The coefficient of t squared e to the 2t is 4a minus 8a once we distribute the negative 4 plus 4a, summing to 0 t squared e to the 2t. And the coefficient of t e to the 2t is 8a minus 8a, again is 0. So we're left with just the e to the 2t terms. And lining up the coefficients, we get that 2a must be equal to 1, since the coefficient of e to the 2t on the left is 2a, while the coefficient of e to the 2t on the right is 1. And this yields a equals 1/2. And thus, our particular solution is 1/2 t squared e to the 2t, and the general solution is 1/2 t squared e to the 2t plus the solution from the homogeneous differential equation c1 e to the 2t plus c2t e to the 2t. I'd like to note that the highest power of t showing up in the homogeneous differential equation is t to the first power, as we're seeing here. We won't need to use any power of t higher than t squared for non-homogeneous differential equations where the right-hand side is an exponential. The t squared in this example is as high as it will go.